Alright, now we have to set up the problem in Fluent, and for that you have to open Fluent from start menu. So you can type first few letters of that particular app and it will open. So first thing is that you have to click on solution. Second thing is you are going to use double precision because the mesh is very fine in the boundary layer. So for higher aspect ratios we should be using double precision. And I have the 4 cores in my CPU, so I'm using maximum cores I have. And then you have to choose your working directory. Right now I'm working in the E folder because already I have the one folder, but I don't want to modify those files. That's why I'm creating new files for demonstrating the same thing on videos. Okay, so right now we are working in the E directory, drive directly. So click on start. So first thing is that we have to import our mesh. Okay, for that you have to go to file menu. And from the file menu, click on read and mesh. And you have to change the mesh type because at the moment the ICM CFD is not outputting mesh in H5 format. It is doing it in the simple MSH format. So you have to choose the simple MSH format and you will see the mesh file immediately here. And now click on OK. And it is around 1,86,000 nodes and a little bit lower than this nodes. We have this number of cells. You can check the mesh size from here. Number of cells are 1,81,000. Number of nodes are 1,86,000. And if you check mesh quality, the orthogonal quality is 0.76. This is very good quality. 0 is the worst and the 1 is the best. And aspect ratio is maximum aspect ratio is 400 around. That's also okay. And if you go to material properties, you will see that we have the air and it has the 1.17894, so make it 1.78. Density is the 1.225, that is okay. Okay, click on change create and close. And in the models, just confirm that the viscous model is SST K omega. That's all we need to make sure. Okay. And then in the boundary conditions, based on the type, you can see we have the 3 types: inlet, outlet, and wall, and also one fluid zone. Okay. So for the inlet, I'm going to apply the velocity at the inlet. This value is 0.1453, something like this. So I will paste everything here. And also make sure energy equation is also turned on because this is, we are going to check the temperature variation. That's why energy equation should also be enabled here. And by default, we have the thermal conditions enabled after enabling energy equation, and the free stream flow, which is going inside the pipe, has a temperature of 300 Kelvin. Just keep it as it is. Okay, then the next boundary condition is that for the wall, heated wall, we have to provide the heat flux. And the heat flux are equal to 50 watts per meter square. So go to the thermal conditions and heat flux, apply them here. It's a 50 watts per meter square. Apply and close. And as far as the methods are concerned, so we just keep them as it is, but initially I will run the case with the first order schemes for every variable here, energy equation in everything. In the controls, I will click on equations and I will uncheck the energy equation so that we only solve flow and turbulence. Okay. And then I will go to the monitors, and from residuals I will be putting some zeros here. Okay, let's see how many zeros we have. We have the 12 zeros, so I will make it 20. And copy this and paste this thing in the every variable. every equation residual plots should be converged to this value. Why I'm doing this thing? Because I want to solve this equation for the required number of iterations until I get satisfied that the solution is fully converged. Okay, so one more thing is that we can also monitor some important variable like the temperature at outlet or temperature on the wall. This can also be done. Okay, let's just leave this thing right now, and then I will initialize solution from the inlet condition. Okay, then I will run calculation for like maybe more than 10,000 iterations. I'm going to provide 10,000 iterations, but I think the solution will be converged within maybe 500 to 800 iterations. It should be like that. I will stop solution here, and I will change all variables to second order, and for that you have to go to methods and change every variable to second order upwind. And then from controls we have to enable solution of energy equation. So click here and click on OK, and then again run calculation. Okay, now solution is converging very nicely. You can stop here, and to increase the speed of convergence you can define time scale factor 10 from 1. So from 1 we are increasing to 10. And also I want to see the contours of y plus, because we have provided the y plus value based on our calculator. This is around 0.00147, but we provided value as a 0.001. So I want to see the y plus values on my model. So both walls should be selected and click on save display. Okay, so you can see that the y plus value is, maximum value is 0.75 and the minimum value is 0.318. So that's okay, and this is within the range of our calculator. So our calculator is working perfectly fine. Okay, so now you can continue solution. And as I told you that the solution will converge within 400 to 500 iterations. You can see it. So I will stop here, and there's little problem that we cannot see the scale here, but I will show you right here. So the radius they are drop up to the -11, and some of them are less than 10 power minus 16. And the reason is that because we have the very good quality mesh and we have the proper boundary condition, that's why we have the good y plus value. That's why we have the very good convergence here. And any convergence which is less than 10 power minus 4 is considered to be the good, and any less than 10 power minus 6 would be very, very nice. Okay, so this is perfectly done here. Now the next thing is that you have to save your file simply. Okay, so maybe the last thing I want to check is again y plus values for both walls, and the maximum is 0.74 and minimum is 0.31.